So welcome. As I just said, you will need a periodic table at some point during this term. And I'm going to spend the first like 5-10 minutes going over the syllabus just briefly. And then if you have questions, you can ask, but usually by the second day, everybody kind of figures out how things are working. This is posted on Blackboard. And if you're having, sorry, I have to realign everything. Yeah, if you're having trouble finding stuff on Blackboard, that's going to be more questions for office hours. So for those of you in this section, this is the 1 to 3 section. I will always be here at 12:30. I can actually bump that time up possibly to like 12:15. And then I will always stay for at least a half hour after. Usually the lectures, I was looking how long they were last year. They've always been 90 minutes, 75 to 90 minutes. So we'll probably be getting done early. And part of that reason, for those of you who were with me last term, is I'm going to be going over the study sets at 6 o'clock every day. So that's why we're going to be actually this time a little bit shorter. So a couple things. This is our outline, tells you what I'll be lecturing on each day and what is due. And of course, this is the first day. The very first lab is a 7-day challenge. There's 3 parts to it. And so that's up there in Blackboard. It's not due until next Tuesday because you have to start it like by tomorrow, because part of it is you have to make a change in your life for 7 days. And Julia and Max and Christian, anybody who's been with me before has done this. And you have the option to even do it. Last summer, there were several people. We have 30 days in the term. So if you want to go for the extra credit, you're going to pick to start today because the term is 30 days and you can do it for 30 days. So if you have questions about that, you can also talk to me. But there's 3 parts to the lab. There's also like a 25-minute YouTube video I made while I was at my mom's. And you can see after today, there is something due. And I made an 8-minute intro video. There is a study set pretty much due every day. That is actually, I found in this virtual environment, and it's probably a change I'm going to keep when I go live again. It actually works. I made the study sets are smaller rather than one big 4-page study set that would take you 4 hours. You have a smaller study set due every day, so we get feedback. The study sets, I think I have mine here. If you can print, my recommendation, you can also do it like on an iPad if you have that, but the answers are there. And so when you do your work, it's math. You've got to do your work. I'm going to be teaching you a unique way to do our work today, and it's got to be in that format. And ideally, you get the answer. If you're not, you can always ask during office hours. But again, every day at 6 o'clock, I'll be going over it. There was a really good question that came up in an email. Would I go over today? On Monday, that's for your study set on Tuesday. It's not due until 6, so you have time tomorrow that you can ask me questions, but you should be able to do it today. And I don't know how long they'll take. And then there's a worksheet. So the study set I will videotape, so you can always go back at your leisure to watch going over it. The worksheet, I will answer questions during office hours. I'll even look to see if you got it. I don't give you the answers, but I'm willing to look to see if you got it in place of quiz. So it's like it's instead of calling it a quiz. And so you can work on it. Yeah, you can have it always checked off. And there's always a bonus on the worksheet. The penalty, let's actually look at the back of this. And the syllabus is posted. A comment I made, I have not been trained on Blackboard. I have the same training as you guys do, which, so I just post stuff on there. But if you turn stuff in late, so this is the syllabus is like in the upper corner of Blackboard. Study sets and worksheets, you lose 1 point if it's turned in late, and they are due by the celebration. So next Tuesday is our first celebration. That's what I call exams, because that word exams is like old news. So anything before that has to be in by there to get credit for it. So your study sets, I've had people in the past and they just said, I like listening to when you go over the study set. And so they just always took the 1 point off for it. And that's not going to make or break you. There's also 1 point of every study set is that you're here present for my lecture time. Labs have a higher penalty. And I need to emphasize that. Labs, you got to get them in. Labs lose a point every day that they're late. And so you got to get labs in, and labs are mandatory, even though this is kind of a funky environment, but it's because the lab is tied to it. And so labs, there's 2 a week. Your first lab is a 7-day challenge, so it's due next week. I think I have this numbered backwards. And so this lab, every Friday there's a lab due, but you can do them before that and turn it in before that. I haven't posted this lab that's due this Friday yet, because I don't want you to do it until I've covered the topic in class, which will either be today or tomorrow. Once I cover it in class, it's a video you watch and you fill out as I go along, and it will take you an hour to at most. It's however long. I think the video is 25 minutes, and so you can pause me and fill out stuff, and so you'll be fine. More for Max because he's here. The lab for next Friday, that's the only kitchen chemistry lab. And so this, usually the stuff for next week, I will post on Friday so you can always see what's there. And I think the other thing that I wanted to mention that I avoided in my intro to you was you do have 2 class projects, which are papers with presentations. So you're all doing 2. One is a famous chemist, and that is actually 2 weeks and a day from today. That is due. So pick a famous chemist. You can ask me during office hours, or you can send me an email to make sure who you picked was okay. 3 people have picked somebody so far. And then in the 5th week, so a month from like today, you guys are all going to be doing a demo or experiment. And so you pick a chemistry demo or experiment, and I help you to refine it. A lot of people will find them like middle school experiments, and then I help you to tweak it to make it more college level. So like changing variables and stuff. So like something they would do for a science fair in middle school or high school, but we take it up. And that was actually a lot of fun last year. I was skeptical how well it would work, and people came up with some pretty cool ideas. Some people videotaped, some people took pictures and embedded them in the PowerPoint. It really depends on what your demo is. So just be aware of those. And the last thing I need to mention is let's just keep integrity up. For those of you who've been with me the whole year, I'm extremely grateful to you because integrity has been beautiful. And last summer I got hit pretty hard and had no idea how well people could cheat in this environment. But this class, you're taking this class, because a lot of you are going into medical school, optometry school, dental school or something. And so it's your learning experience, and let's just do it honestly. And again, office hours, it says 12:30. I can bump that up a little bit, and I will always stay after. I also reopen the evening link always from 5 to 6. So you can always take a break, work on stuff that's due tomorrow, and come back and like be ahead of the game. Is there any questions any of you have for me? That was like a real quick overview. And
so
all right.
If there's like, if I want to check my study set and I go to like the 6 o'clock class, can I leave just right after you're done with?
Oh yeah.
Okay.
Yeah. Absolutely.
Sorry, I got one question. If I can attend the 1 to 3, I can attend the 5 to 8. That's the same thing.
Is that major?
Yeah.
Your voice sounds different.
Yeah, we just got back we're partying all weekend. That's why I'm a little late, but it's just gone.
He's honest about it. Yeah, so officially the evening class is Tuesday and Thursday. And so on Tuesdays and Thursdays, I will be lecturing both from 1 to 3, and I'll be doing the exact same thing in the evening. And I put in my email actually that I will absolutely do it all 4 days of the week. I have no problem lecturing twice 4 days of the week. So basically you could come either from 1 to 3 or 6 to 8. The only exception with that is the study set. I'm only going over once a day, and that's going to be at 6 o'clock. And so both sections, the study set is due at 6 o'clock, just to make it easy for me. The study sets are due at 6. And study sets are graded that you made an effort. Even if you got a question wrong, as long as you made a good effort and it's there. Worksheets are graded that you made an effort and you got the question right. Each question is only worth a point. And they're to help you get ready for the celebrations and stuff. And the worksheets are always due by midnight. But again, you should be able to do the first study set and worksheet ideally tonight. It's always due the next day, because sometimes once I do the second half of the lecture, that helps fill in some of the blanks, the pieces that you might have missed. The other reason I have something due like a study set tomorrow is it actually enhances your experience of the lecture tomorrow, because by me kind of forcing you to do some work tonight, tomorrow morning, before you come to class, it means you've at least thought about chemical equilibrium a little bit, and it will help you to hopefully understand more of the lecture, the second half of every lecture. So most topics you can see that we cover, we spend 2 days on each topic. The other thing I should mention, this week's folder is not complete. There is a second half of the folder, which I will be opening, so you can print all the stuff for later in the week. And it's just that I like to meet my class. And was there any other questions? Did I answer your question, Major? Oh, so just a real quick comment. It's really hard for me to teach and do the chat thing. So I don't know if the person who sent me a chat, if you can talk, it's easier for me to hear, or I'm just not capable. My brain can't do it.
Actually, it's okay. I just posted for people who would like to join the study group, so it will be, more easy for us to connect. So it's not for you, just for students who would like to make a study group after the class.
Okay. All right, so let's go ahead and start with chemical equilibrium. And again, having a periodic table handy will be useful. Can't wait to be able to be a full person again. So this whole term builds on today's lecture, and it is that we revisit a lot of the subjects that we did in previous terms, like thermodynamics, oxidation, reduction, and we finally get to embrace acids and bases. And it is because all of them depend on this idea of the double arrow. And so it's kind of like your teachers, we've all been lying to you for the past few terms, because reactions, we always showed them with one arrow, and we could do stoichiometry and we could do the factor label math, and it worked beautifully. It turns out most reactions, which is a good thing, actually go both directions. So think about it. Our bodies are chemical equations. And so we have to find that balance point. And so being able to have things go two ways, and that's what equilibrium is that reactions go two ways. So terminology, how the equation is written, the reactants are always written on the left side. So I am not going to use the term left and right, partly because I am flipped from you guys. I have to do that so you see me correctly. And also because dyslexics have trouble with left and right, which we all have that issue. Whereas reactants and products work much better. And so we're going to use those terms, reactants and products. The other way you'll see it is whenever you're moving in the forward direction, that is called the forward reaction. And when we're going backwards, that is called the reverse. So reverse means also toward the reactants. So sometimes we just say R for reactants and P for products. So those are going to be the terms we use. You will, I think how I have it, I think how in my Word program it shows the arrows like this. You'll also see where the arrows can be written like that. That's the classic way of showing it, where you show 2 half arrows. It really doesn't matter. These are questions students have asked me over the years. They mean the same thing. And so it's all about finding the balance. Now, equilibrium doesn't mean that the amount is equal. What equilibrium means, what is equal at equilibrium, is that the rates of the forward and the rate of the reverse are balanced. So that's what's equal. It's not the amount. Okay, the other thing, before we go into the expression, is something else that's assumed for equilibrium to be there, and this is the key. All components must be present. So all reactants, all products have to be there. So when we initially mix 2 things, so let's say I'm doing this reaction and I initially mix the hydrogen and iodine, I am not at equilibrium because all I have is the hydrogen and the iodine. Chemical equations, chemical reactions, does anybody know how fast they happen? Somebody might pick this guy as their famous chemist. There's a guy who came out with the idea of femtochemistry. Most reactions happen in, like a slow one would be a nanosecond, but most are happening in femtoseconds, which is, does anybody know what a femtosecond is? What fraction of a second? It's 10 to the negative 15. So like 15 zeros of them per second. So as soon as you mix, what I'm saying is as soon as you mix these 2 things, they're going to react to form the HI. However, what is different about equilibrium from what we've always been doing is that you just assume they react and they make HI, end of story, we're done. What's going on is as soon as it forms the HI decomposes and goes back and makes them. And so it hits a point where they're both reacting. And so as the one's reacting, you start with a certain amount of hydrogen and iodine, right? So you start up here with, you have all this hydrogen and iodine that you start with. You don't have to draw this graph. It's like in every book. And they react. But then they hit a plateau because you have initially no HI, but it reacts and you end up with it. So what I'm trying to show here is the amount you have doesn't come out the same. And that's what we're going to talk about here, which is the key. What comes out the same is the rate. That if we did a graph where we showed the rate of the forward and the rate of the reverse, we would see that they hit the same point. So if we did rate in the green, they would hit where they're reacting equally so that the concentrations no longer change. They get to their point where they are at equilibrium and they no longer change, but they're all present. Nothing is a zero. You don't have any zeros. That's actually really important. All right, and then one other piece, well, as we go through this, it is temperature dependent. And so you're going to see in a lot of questions, and when you study density, you might remember this and some other stuff, like in this question, that you're going to see temperatures given. Almost all the time you can ignore the temperature. There's going to be sometimes when we'll want that temperature, but it's not that it's extra information. It should be in every question. I've just taken it out of some questions because some students, it confuses them. All right, the key to what we do is this. It is called the equilibrium constant expression. Everyone calls it just the equilibrium constant, and it is symbolized by a capital K. So when you did kinetics, use the little k to talk about rates of reaction. There is a way that they are related. And so when you take biochemistry, you actually get to do a lot with these. But this is something we will be using all term, is that K is always, it's a ratio. And it is always products over the reactants. So for our equation that we have up here, if I was going to write the K expression for that, I would write K equals, and then I would say my product, HI, And the power, that P out there, is going to be to the second power. So the power is the coefficient, or the exponent is the coefficient. So if you remember the coefficients, or coefficient, if you've been with me the whole year, so since there's two HIs, so that's in our numerator, the product. And so that's why, however the question is written in that question, I want to emphasize that again, because you're going to see this equation probably again. Some of the equations keep showing up, especially in these first 2 days, because we're just getting the basics. However it is written in that problem, that's how you keep it. All right, and then we do it over the reactants. So hydrogen in its bracket, and then times iodine. So it is all multiplying and dividing. In the equation, we showed this plus this react to give us this. Here it's a ratio. These had no coefficients because they would be to the first power. And that's it. That's the key. And then we can mathematically plug numbers in and get a number here. And that's where we're going to be going with the rest of this. So one more piece with this is units. These are brackets because brackets actually have a meaning to chemists, to scientists. And so with that, your teacher is going to eventually just show parentheses, because normally I was writing at the board and my arm would get tired. I'm okay with using parentheses. I just want you to know that technically it is a bracket, the square brackets. So initially we'll all show it that way in the notes, but the brackets indicate capital M. So hopefully you all remember what that capital M stands for. Anybody?
Molarity?
It is molarity. Major, there you are. And what does molarity, was that Captain Max? I don't know who said that. But do you remember what the units are of molarity?
It's 6.02. I don't remember from the top of my head. It's to the
So
power.
that's Avogadro's number. That's something totally different.
Oh,
That's
okay.
a really good comment, and it made me realize I don't know if we get to use Avogadro's number. Oh, we do. I think later in the term, but we don't use it this week at all.
Oh, okay. I got confused. Molarity was something else. Sorry.
Can I
It's
try?
been a while.
Go ahead. Elizaveta.
Grams divided on the milliliters?
Moles per liter?
Yes.
Yes. And so this is actually really important. So I have moles per liter. You can abbreviate moles as MOL, or you can write the whole word out. Molarity is a capital M. And so please use your symbols correctly. And then this, or you can write it as moles per liter. That's actually really important because whenever we plug stuff into K, we have to be in these units of moles per liter. So keep that in mind. You can also use, if it's KP, then the units are ATM. The P stands for pressure. And so if you're dealing with gases like here, you can see this one's a KP. So then we use ATMs as our units. And so those are the two units that we use. So with that, there's one other piece. For K, you only include, I seem to be stuck with one color pen today, aqueous. So aqueous is going to be molarity. So moles of the solute per volume of the solution. Remember doing that. And gases, which typically are going to be in ATMs, although we can change them to molarity if we needed to. So you do not, you eliminate, when you write the K expression, you don't include solids and liquids. The reason for that is the solids, they're a mass. If they're a mass per volume, that means they've become aqueous. But as a solid, they don't have a concentration. And for liquids, pretty much the only liquid we see is water. And the amount of water present is in so much excess of everything else, it's just never included in the expression unless it's in the gas state, and then it's a different thing. So water's there as part of the aqueous. And so we'll see that actually we're going to write the K expressions for this. So you only include aqueous and gas. However, with that, to truly be in equilibrium, everything has to be there. So when we look at this example 1, our reactant is a solid. And so what a lot of students will do is lightly cross that out because it doesn't impact our K expression. You have to have solid there to have equilibrium. So if we were in the classroom, if we were in the lab, to be at equilibrium, you would have to look at your test tube and there would have to be floaties in it, meaning you have solid in there. It'd have to look like a snow globe. And so it was actually the lab we would have been doing tomorrow, that you guys add stuff and you keep adding until you see the floaties, because until you have the solid present, you don't have equilibrium because everything has to be there. It's just the amount of solid doesn't matter. The amount of aqueous does. So for this equilibrium expression, we would just say K equals. You do show the ions as ions. So magnesium with its +2 or 2+, it doesn't matter to me if you show as a +2 or 2+. That is not a coefficient, that's a charge. So it's inside the bracket. And then times the hydroxide. And then the hydroxide is raised to the second power because, again, the coefficient. There is no numerator because it was a solid. So we just write it like this. There's always somebody, more than one, who wants it to always be a ratio. So you would just show it over the number 1 because there's nothing else down there. You don't want to put it as 0 because that's impossible to do. So that's what I mean. So the solid and liquid have to be there. They're part of the equation. They have to be in the test tube or in the flask or whatever or in your body, whatever your experiment is. But when we write the K expression, they're not part of it. And so on the next one, whenever you see solids and liquids, this was actually something students have shown me a trick that to lightly cross it out. I mean, don't like do it with a black pen so you can never see it again. Using pencil is a wonderful thing. And that way you remember not to include it. So to write this K, we do K equals, here's quick questions. So, and I do give bonus points if you can answer the full question when I ask it during lecture. So bonus point is always fun. Does anybody know the name of the ions? You'll all know them by the end of this week. Say that again.
Is it peroxide?
No, peroxide's H2O2.
Oh,
we're gonna see that.
The hydronium.
This one is hydronium. And you know the other one, Major?
Acetate?
Yeah.
Oh, no.
Wait, Major, did you say hydronium?
Yeah.
Okay, so that just gave me an ego boost because I was the one who taught him hydronium back like 2.5 years ago in Chem 104. So I'm like amazed that you found that deep in your recesses, especially since you were partying all weekend with all your buddies. And I don't know who said the acetate, but yes, that is acetate. We are going to, starting Wednesday, we're going to be doing acids and bases, and hydronium is the key. So you're all going to become familiar with hydronium and hydroxide. And so I'll mention that. And this is acetate. I wanted to mention this also because it's a question some student will ask me. Acetate ion is shown different ways, depending if your teacher is a biochemist, which I am, or a general chemist. And so sometimes it's shown as C2H3O2 negative. And I mention that because like in 221, if I mention this, students freak out and they're like, well, which is it? hopefully by now that you're in 223, you go, oh yeah, they are the same thing. So the advantage of this way of showing it, how I showed it, is it's trying to show you how the structure would be. You've all taken 222, so you've done Lewis structures. So it's saying it's a carbon with 3 hydrogens and then a carbon with 2 oxygens. So when you take organic chemistry and biochemistry, it's more structural. General chemistry, it's more, oh, we just care how many carbon, hydrogens, oxygens are there. Anyway, that's extra information, but just something, because it's a big picture thing, all the little details. But how we'd write this, hopefully you already did it. That's also me babbling, so you can write it. You write your ion, the acetate, and then the hydronium, no exponent. Again, it is multiplication. And then our denominator is acetic acid. So CH3, CO2, H. And that would be our ratio. So that is the key to what one of the things today is products. It's always the products over the reactants. You leave out solids and liquids, and the exponent, the coefficient becomes the exponent. What we're going to do now is move into the math where we'll plug in numbers, and then we'll see how a new way to do math. All right. So this problem has a keyword, 2 keywords at the beginning, and it's something to keep in mind, because I'm going to show you a new way to do math on the next page, and everybody will miss this later on. If the question tells you you're at equilibrium, then you're there. Equilibrium's been established, and you're ready to go to use your K expression. So we're at equilibrium. This is how much PCl5 I have, so 0.860. I just like to write it underneath my equation, so I know what I have. My PCl3 is 0.350, and we want to know how much chlorine, so that's my question mark, right? All right, this is at equilibrium. That's important. So we're ready to go. The first thing that we have to do, so your celebrations, your worksheets, your study sets, it's all about showing your work. My colleagues have told me, they're like, yeah, if I do this all online again, I'm going to do like you did and make them have to show their work. And so you need to show your work clearly. And again, the whole term builds off of, it keeps building off each other. So set the study habits now. So you're going to always first state your K expression with the compounds from the equation. So we would have K. I kind of pause. So those of you who know what you're doing, you can kind of keep going and see if you got it. So products, PCl3 times the chlorine over the PCl5. All right, so that's what I mean when I say, please write the equilibrium constant, is that you're just stating this. Every problem you solve, this needs to be stated. Now we're going to plug in. So if the K is given, about half of the questions are going to ask you to solve for K. So you're going to be plugging numbers in. In this case, if K is given, it's given after the equation, usually like this. And it is also important, if it is a KP, it will tell you that, which means that you're using ATMs. If that P is not there, it is technically called a KC. So C stands for concentration. And so they usually leave the C off because it's almost always concentration. All right, so we're going to plug our numbers in. You can rearrange it and then plug in, or you can plug in. So 0.35 ATMs. We can put the chlorine as our X or whatever, question mark, 0.860 ATMs. There was another comment I needed to make. Fascinating to see how my brain works in this. So we're going to go back a moment, back to the middle of the page. And it is up here when I talked about equilibrium constant. In my class this summer, which you are all currently in, our equilibrium constant in my class, we're going to do no units for K. What you're plugging into K has units, but K itself does not. If you remember when you did rate laws, that K always had funky units, and the units are different depending how everything crosses out. Those of you who are going to take biochemistry, you're going to get to do equilibrium, and usually your teacher is going to want you to show the units, and that's great. You can show the units. I just leave them out because it complicates things, and then we miss the big picture. X is going to have units, and the units are going to be ATMs. All right, so you would rearrange, solve for X, right? So we cross multiply, so you'd multiply. So for you guys, showing your work. So let's say this is the problem, showing your work. What I need to see is you would state your K expression, you would show me how you plugged in, and you would give me your answer. There we go. This, by the way, how I wrote this answer, it's P and then a subscript, so it just says P and then it says Cl2. That is the symbol for partial pressure. A lot of people never quite get that back with gas laws, but it's saying the pressure of the chlorine is, and sometimes my answers are missing units because Bill Gates and I struggle with my formatting. So good old Uncle Bill. It will have a unit. If it was K, you leave the unit off. But some of you have calculators where you just plug it in just like this and it solves, and that's fine. Some of you can rearrange in your head because of your math skills from 7th grade or whatever, and that's fine. And some of you are going to show me how you rearranged, and that's fine also. But I need to see the statement, I need to see what you plugged in, and I need to see your answer. Most of the problems are going to have more steps than this, but there's always somebody who has trouble with the rearranging. This is just cross multiplying, so the 0.86 moves up and the 0.35 will move down below, right? So you'll divide by that. The ATMs technically are going to cross out, but then we're left with ATMs. Any questions with that?
I did the,
Go ahead, Paul.
yeah, I did the, I divided basically the first section, the 0.4 with, divided the 0.350 by 0.86, and then divided
Yeah,
the
that's fine.
result with the other. So
Right.
it'll work, you'll come up with the same answer either way, right?
So you're dividing by the 0.86 double, which just means it moves to the top. It's the double inversion rule. So it's fine. Yeah. Yeah. That's why I said I don't necessarily, how you plug it in your calculator doesn't necessarily matter because we all learned those things different. If you're having trouble, there's always some people, like I was very skilled with algebra, but there's always some people, and so that's why I have office hours, so we can refine some of these things. A quick comment, whenever with most of this, the problem solving, usually what you see after in parentheses, like on the study sets, those are the answers, and I'm pretty sure all my answers are good. Every once in a while, I have a typo because I changed the problem and forgot to fix the answer. So if you're like working on these at home and you're not getting mine, or you're working on it as I'm talking, please let me know and we'll figure out if my answer is incorrect. Any other questions from this first page? Sorry, this is something, all right. I can't see a clock on Zoom, and so I have to keep track. I'm used to in the classroom, there's a big clock staring at me, so I can manage my time. All right, so this is also a quick comment, just remembering from the fall, I had a class and they loved chatting and stuff. And they were like, oh my God, I didn't print the notes. Oh no, what do I do? She's going through the notes. Just take notes. I had some students who were extremely successful. They've been with me for a couple terms, and they said they never took notes during class. They just sat and listened to me. And I'm like, really? And they said, yeah. And then I would go back later and listen to the video and I'd fill in the notes. But they said that was, or they might write like one thing down. So kind of remember that I am recording it, that you can always go back and fill in the gaps that you're missing. But do ask questions. I am greatly appreciative of these questions, as are your classmates, whether they're here now physically or they're here now listening, because it really is the same thing. That's one of the miracles of Zoom. All right, this is a moment I keep alluding to, and that we're going to learn about ice charts. And I could not, for those of you who've been with me, I couldn't figure out how to make myself into a giant ice cube. But and I'm bummed because I did offer if you're going to wear your NOF today. But I couldn't figure out how to make an ice cube NOF. If somebody can for tomorrow and wants to fashion an ice cube as their hat or their whole costume, that would definitely be worth a bonus point. All right, so we're going to make ice charts. So this is how they work. You're going to have the equations. They're always given over, like under, I give like blah, 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 writing questions. And then I give your equilibrium equation. However I give the equation, the reactants are before the arrow, right? And the products are there. However it's given for that question. And then to the left of them, you write down ICE if the question doesn't start like the previous one where it says we're at equilibrium. Notice I just started right at E, which is what the E in ice means. E is equilibrium. I, it tells you up here, I is initial. So what initial means is that word, mixed. It's what you mix together. So if you guys had been in lab, last year when I got to teach this, those people all at least had some lab experience. So there's a couple of you had Dr. Russell a year ago. So you actually have that idea or major, like you mix things together in the lab. So these are the things you mixed. They're going to be the I. And then what I commented up here, it has to be molarity. Unless we're doing KP, if it's KP, then it's going to be in ATMs. But we're going to do molarity for this whole page. All right. Sorry, I haven't figured out my chair again. I figured it out at the end of last term and then I rearranged. And so I keep sinking as my pillows get flattened. All right. So, all right, so information given. We have this many moles of hydrogen. You can write it as the exponent, how I have it there. I often like to change it to like without the exponent, so 0.005 moles. And then we need per 5 liters. I always write it, the information that's given in the problem. You can change that to molarity if you want. And the iodine is 0.0100 moles. Sorry. I'm usually at the board, so I get to write bigger, and I have yet to learn how to write small on a piece of paper. When I'm teaching, I think big. All right. So that's my amount of hydrogen and iodine. It doesn't say I mixed any HI, so that means it's 0 initially. And so we can't be at equilibrium because you can't have a 0 at equilibrium. So whatever you mixed is your initial. All right, C is for change. And change is based on the stoichiometry, the coefficients. So our reaction, to make it to equilibrium, it's going to have to move forward initially. It's the only way it can go. You always are going to go towards the 0. To reach equilibrium, the reaction has to move towards the 0. That's important because it tells you that this side is going to decrease, and we're going to just call them X. And the other side is going to increase. And that side's going to be a 2X. The reason it's 2 is because of this 2. Not because there's 2 x's here, but from the stoichiometry. We're going to do more practice of these, and that's why you have a study set tomorrow, because you have to try it, and then we do these all day tomorrow with different twists on it. All right, so at equilibrium this is going to be what, 0.001 minus x. That's my molarity. So once I start including the x's, I leave my units off, and then I'll put them back in once I solve for x. This is right, 0.002 minus x. So what it is the initial plus the change will always give you your equilibrium amount. So this is going to be this minus x, this minus x, and this is just going to be 2x. So these are my equilibrium values. All right. So that's the ice chart. We have to figure out what x is. And, oh, actually, there's one more piece of information. Is that it tells you when you're at equilibrium, this is how much HI you have. And so a comment that I usually make at some point, it's really nice to have multiple colors. So you can kind of highlight things, and like some of you have iPads and stuff, and so using different colors. So my students tend to start getting more and more colorful. So what that means is this is going to go under here at equilibrium. So the 2x must be equal to that number, which is the 0.00187. And that is molarity. Oops. So I don't have to worry about volume. So units are really important. In your chart, the chart must have units. So let me put a note for you. Chart must have units. There's kind of a joke amongst my colleagues that I'm a stickler for units, and there's a reason for that, because if you don't show the units, then you're not going to get it right. When we're solving for x, which we're going to do now, you can kind of, this one's not a tough one to solve for x, but we're going to, at this point, we're going to go do 2x equals 0.00187, right? Divide by your 2, and you'll get whatever that is, 9.35 e to the negative 4. And that is molarity. That's our x. Yeah. All right. Once you have x, every problem is different. So the steps we're going through, make your ice chart and then figure out what you have to do. So from this one, from this step, I could solve for x, and then I'm going to go from there. So now that I have x, I can go back up here. I can solve for these two numbers, and then I'm going to pause in a moment because I'm going to have you guys try this. We're going to solve for k. So on this problem, I could use the chart to solve for k, to solve for x, and then I solve for k. So at some point, you want to write your k expression. So remember, write out your expression. Then you're going to plug your equilibrium numbers in there and punch it in and solve. So I'm going to pause the recording, and I want to give you folks a chance to try that. And if I figure out how to do this. So during the break, Elizabeth was asking me a question, so I wanted to comment on your lab 1. I don't know if I call it lab, it's the lab on acidosis, and it involves a 7-day challenge or inspiration. So we'll say a 7-day change that you have to do. So normally on Wednesday, when we get into acids and bases, I usually have a half hour to an hour where I talk about acidosis and how crappy the American diet is. And the American diet has gotten crappier, and it's gotten even worse with COVID. But and it's sent us all into systemic acidosis. And so you guys, so I made a video of that, so you don't have to listen to me go on for a half hour to an hour, but that you're going to make a change to your diet for 7 days, which you have to get rid of the crap. So you can figure out what that crap is. So if you're like, I'm laughing because Major works at BlackRock. So if you're somebody who you can still have coffee, but you can't like have the coffee how most people have coffee, or if you're somebody who does fast food, so some people like gave up the fast food for 7 days, or you can do the no animal products, because the cause of acidosis is sugar, processed food, and animal products. And so you're going to give up something. It's 7 days. You can do it and just see where it goes. And then you're going to tell me how it went. And it's a way I get to know you. There's 3 parts to it. So besides that change that you're going to make for 7 days, you have to start by Wednesday because it's due by Tuesday. But if you started today, then you can always turn stuff in early. That was a question. I can't remember who asked me this in an email. It's something I learned on Blackboard the first term, that I put a time that things are due and everybody turns it in at that time. You can turn it in early. If you get the lab done for Friday early, you can turn it in early. Or this one, if it's done Monday, you can turn it in Monday next week, but you have until midnight Tuesday. You're going to have to watch, there's a video. I give you 5 choices of videos. You get to watch one of them and you just write comments about it. And then you have to make a new recipe. So hopefully whatever your change is, I give you a website. You have to go in there and just try it for 1 meal. So it's you in your kitchen, because cooking is chemistry. And so if you have questions, again, you can ask during office hours and stuff, but please make sure you look at that lab in the next day or 2 so you can get started on it. There will be another 7-day inspiration lab next week that I'll be posting this weekend that is different from this one. Those of you who've had me before, you probably know what it's going to be about because you've done ones. I can relate these labs to anything in chemistry. All right, let's go ahead and solve these. So you want to have your ice chart. I like to do arrows. It's actually, I smile sometimes because it brings back memories of previous students because it tells me where I'm going. So this number, did I write down what the numbers are? This is going to be like, I don't know, 6.5 e to the negative 5. Yeah. So you're taking the 0.001 molarity and you're subtracting this number x. And this is going to be 1.665. So we're going to talk about Sig Figs for a minute. E to the negative 3. All right. Let's talk about Sig Figs. Let's talk about it up here. All right. So back in 221 and 222, and like your teacher got to teach you about Sig Figs and got to be a stickler about it and say Sig Figs or significant digits or whatever they called them. And those of you had Dr. Russell, I'm laughing because my son had Dr. Russell last term. And holy moly, he is a stickler. I'm recording this. I hope everybody can go tell him I said this, because I've had a bad rap that I was a stickler. He's really a stickler for it. So Sig Figs are a little unusual in chemistry 223 because we're going to get into pH this week, and pH is a logarithm, which means we're going to be doing functions on our calculator. And when you're doing functions, it's a whole new rule for Sig Figs. So we're going to try to appreciate them. If you want to go with the physics rule for Sig Figs, and I absolutely love this rule at physics when they teach you physics, and you want to just give everything 3 Sig Figs, I'm okay with that. And so you're going to see me sometimes doing that. If you want to try and follow the Sig Figs, that's actually here I did, and respect it, then that's great. You'll see sometimes I'll give you like 8 Sig Figs that you can use, which is a little ridiculous. And so you're going to see me usually just go with 3 Sig Figs. If you do have questions, you can ask. I often just keep these numbers in my calculator, and so that's why I'm having to look at what they were. All right, so these are going to be, and this, of course, is this number. So these are the equilibrium values. These are what's going to get plugged into our K expression. So we want to write our K expression, which is products, the HI squared over the hydrogen and the iodine. Again, I am perfectly fine with parentheses. It's supposed to be technically brackets. And then we plug in. So K equals, you do have to show me what you plugged in, the 0.00187. I recommend you put a unit because that helps you to remember that, yes, I am in molarity. Your chart has to have units. When you solve for X, you can leave the units off. When you do K, I'm going to make it optional because we're going to end up canceling our units anyway. And then this is, remember to square the top number, 6.5 e to negative 5. You can write it, just real quick, you can write it with a whole bunch of zeros, or you can change it to scientific notation. That's really up to you. There is a point when you want to show it in scientific notation, like this one, because there would be too many zeros. All right, you punch it in and you should get my answer that K equals 50.5. You're going to see, again, for those of you new to me, and I lost this. There it is. On the study sets and the worksheets, there's going to be boxes. On the worksheets especially, that's for you to put your answers. So I can see, it also helps you to know, yep, I got my answer here. And so it's just a nice place to show your answer. All right, so this term is very unique how we show the work. You have to be very clean in your work because there's a lot of stuff going on. So you're going to see I'm going to make the ice chart over here on the left side underneath my equation, and the K expression and what I'm filling in is here. The arrows can be helpful or numbering your steps. Every problem's a little bit different. All right, on this one, I tried to show you on this page different ways. That little I means initial, so it's telling us the initial amount of the SO3 is the 0.00609. Again, the chart has the units. That's the only initial I give. And I go ICE. And then the equilibrium amount of the SO3 is 0.00244 molarity. All right, that's all I give you. At equilibrium, there are no zeros. Initially, you have zeros. So if I didn't give you anything for the initial, they must be zeros. My equilibrium has, my equation has to move forward to achieve equilibrium because I have to have everything there for equilibrium. So showing this arrow is a key because this, if I start, and I do on the next one, sometimes I start you with the products. That's just meaning our reaction is going to go backwards initially. All right, the key is the x's. So since we're moving forward, this is going to be minus 2x. This is going to be plus 2x. This is going to be plus x. So the change is how it changes based on the stoichiometry. So we have a 2, and if it's a blank, it just means it's 1. Whichever way the reaction is shifting towards the zeros is the plus side, and the other side is minus. All right, we have to have a complete E column to be able to solve. So once we solve, right, we'll write our K expression is SO2 squared times the oxygen over the SO3 squared. All right, so that's going to be the expression that we're going to plug into. It has to be the equilibrium numbers that plug into there. So to do that, I have a full column. If you have a full column, then we can use that. And again, it goes back to this. I plus C equals E. So we have that 0.00609 minus the 2x equals 0.00244. So basically, I'm taking that part, I'm going down here to solve for x. Once I solve for x, then I can finish my chart, and then I can go over and plug in. Every problem is different, and so it takes practice. Last year, I had a student who was extremely successful on the first exam. I had a student, and so I had one student who got an A. Actually, I had two students who got an A, and all the rest got B's and C's and D's, and some of the students were like, ah, and this happens every year. And it's because the math is unique. The students who got the A on the first one, and then the others started to, is they said they went back and redid the notes. They would have the video there and listen if they had to, but they would print the notes a second time, and they would try the chart again because it takes practice. It doesn't mean you need to do it tonight, but like sometime that you want to go back and try these and make sure that you have the idea. But that's why you want to do your study set and see, and if you're having trouble, you can go back and look in the notes and see if there's a problem that's similar. All right, so you're going to rearrange and solve for x. So, right, you're going to subtract the 0.00609. Back to like Paul's question. Well, let's go ahead. I'm going to go ahead and go through. So to move this over, I have to subtract the 0.00609. And that's going to give me, sorry, negative 0.00365. That equals negative 2x. Then we would divide by the negative 2. So because these are two separate terms, remember you have to move the 1 and then isolate the x, and then further isolate the x. So for some of you, it's the algebra is going to initially get you, and some of you are like, I have no problem with algebra. Don't just come to office hours and say, hey, can we go over this problem again? Or I'm having trouble with this one. Can we go over it? And sometimes it is just walking through the algebra with me. And then we would divide by the negative 2, and we get that x equals, x has to be a positive value. The change can be positive. The change is positive and negative, but the value of x is going to be positive. And so we get x is 0.00183. Now, again, when you're solving for x, you can leave out units. In the chart, though, at this point, for this first week, our chart is going to be molarity. Unless we're doing KP again, then it's ATMs. So in the chart, you do have to be in molarity. That does change next week, but let's just stay in this week for now. All right, so we find x. So now we can go up here and we can plug in. So this is 0 plus x, so this is just going to be 0.00183. And I put a unit because I'm back up in the chart. And this one's going to be double that unit. So some students' arrows help them. What's that double? 0.00366. Just a reminder again, you can show it with the 0.00, or you can put in scientific notation. To me, that doesn't matter until we start getting like 5 zeros. Then you want to use scientific notation. Then you'd plug into K. So this one, I'm going to walk through all the steps again, and then I'm going to start taking some shortcuts at some point, just in the interest of time. All right. And then you just plug in. So 0.00366. Remember to square that. That's probably the most missed thing. So when you plug in, take a deep breath, plug in, make sure you remember. That's why you're always stating the K expression. Our oxygen number, 0.00183, running out of space. And this one. And you plug in and you should get my value. All right, questions? All right, the next one's a little bit different, but we're going to go through the steps. So you write your ICE chart. So you just write ICE. I think I usually have this shifted more. I think my printer, yeah. And at some point, you're going to write your K expression. I usually do that over here. Right, this one's going to be a little bit different. And I want to walk through this one. And that is because I gave you the value of K. So that we're going to be able to plug in right away. But we're going to deal with the ice chart first. So it tells you how much is placed in the flask. So 0.35 moles of the IBR. And I gave you 1 liter. So real quick, Sig Figs. If you want to respect Sig Figs, which I apparently did in my answers, since I only gave you 2 Sig Figs and you want to keep it 2 Sig Figs, that's great. If you want to go with 3, that's great. I'm happy with that. All right, moles per liter. Our chart needs to be moles per liter. I am not technically correct there, but we're going to do it this way for the first week. And then next week we'll refine it once we've mastered these charts. Keep it in molarity. All right, that's all I know for my chart. That's all I know. We're trying to find all these numbers at equilibrium. So there are zeros. Where are the zeros? Anybody?
They're on the product.
It's on the reactants. If you don't have something initial, you have zeros. So zeros can only be in the initial. So let's go and write that at the top of the page. This is where you can have zeros. You cannot have zeros at equilibrium. If you have a 0, you're not at equilibrium. All right, my door doesn't latch, so. And by the way, sometimes my headphones, I have to wear the headphones or else I hear too much background noise, but sometimes they do weird stuff. And if they start doing that, Maddie was really good last term telling me when I started having weird robotic noise, let me know, and we'll figure it out. All right, so this is actually the question. Which way does the arrow for the change go?
Reverse.
It does, because that's the side that has the zeros. So I had 1 year when I started showing this arrow, I didn't show it 25 years ago. It was like a big game changer. Equilibrium, these are called the reactants, and this is the product. So for our K expression, it's however the equation is written. But when you mix stuff, that's where it is. So
Sorry,
my
your headphones
product
are
is going
acting
to
up.
be, go ahead, what?
Your headphones are, they were lagging.
Are they okay now?
Yeah, they just lagged for a little bit, but it's okay now.
I think I hit it with my pen, and that
Okay.
was why. All right. So the plus is not always on the product side. It's the plus is whichever side had the zeros initially. These are x's because there was a coefficient of 1, and this is minus 2x because of the coefficient. All right, so at equilibrium, this is 0.35 minus 2x. This is x, and this is x. That's all we know from the chart. This is my K expression. So I'm going to plug this into my K expression. And I know K. So I'm going to plug the K into my K expression. So 280 equals the 0.35 minus 2x squared over x times x, or x squared. Now, so questions to that point. Now we have to solve for x. And then we can finish our chart and then get the numbers that I have here. So I give you what the value is. So I want to go through a couple of things here. About half of you have calculators that will solve for you, and that is perfectly fine. If you have a calculator like that and you know how to do that function, you're going to get 2 answers because it's x squared. You're going to tell me I solved using a TI Inspire. You give me the two answers. The one answer is going to obviously be wrong, and we'll talk about that more later. Just in the interest of time, I got to move on. If you do not have one of those, have no fear. I have like the simplest calculator there is. I have a $15 one. We can get rid of the square. It's actually easier to not have one of those because we have a square on top and the bottom. So you have to square root both sides of the equation. So you're going to have the square root of 280, whatever that number is, equals, when I take the square root, I just have 0.35 minus 2x over x. So you have to square root the top, the bottom, the left, the right. You square root everything. Then you rearrange, you move this x over, you combine, you solve for x, and you should get this number for x. So all those steps, that's a mathematical thing. And so if you're having trouble solving for x, just please stay after class and say, hey, can we just spend like 2 minutes and can you walk through the algebra of how to do that? Again, you have to move the denominator over and then rearrange, solve for x. And we'll do that. So a quick comment. I think well, for you guys, I've been generous for time. It just takes practice. We all do math in our way. If you are somebody, again, if you have the solve function, you would tell me, I solved using a TI-89. These are the numbers I got. If you don't have a solve function, you should be showing me this work, which again, I usually have the board, right? You would show that you did the square root of 280. I don't know what that number is. Equals 0.35 minus 2x. You would move the 2x over to this side. You would combine them and then solve. And you should get that my number up there is whatever it is. So you're going to show me a little bit more work. I actually don't find there's any difference. I find that the students who copy off of other people are the ones who can't do it on their own in a situation. So just do the own work. And if you're having trouble with the algebra, just during an office hour, say, hey, can we walk through the algebra on this problem? And we'll do it. And usually that works out. So I think this comes out as 18.7 x equals 0.35 once you punch that like in, and then you would divide by the 18.7, and that's where I got that number, apparently, up there. The calculator is in a funky mode. Yep. Again, I just went with 2 Sig Figs. And any questions? All right, we're gonna move on because there's a couple other things, yeah, we need to talk about. All right, and that's why you have a study set tomorrow, because you have to play with the ice charts. So for those of you in this 1 to 3 o'clock time, please realize your study set is not due until 6 o'clock tomorrow. So you should be able to do it today, but we'll be doing more practice tomorrow. We're going to be doing more of the notes. And so try the study set. And then if you're still having trouble, you can come to lecture. And then by the time we get done with lecture, you should be able to do it, no problem. Or come to office hours or stay after today, even if you want to work on stuff. We're going to talk about, there's a couple other things we have to do to allow you to get through your study set. That was the hardest page. So, K tells us something, and this is actually one of the big points of the term, is what the value of K tells you, because K is a ratio, right? It's products over reactants, so it's always P over R. It's a ratio. K is not going to be equal to 0. The amount of something you have can be 0, but K is a balance point. You're either more than 1 or less than 1. That's important. It cannot be a negative number and it cannot be 0. So K is either greater than 1 or less than 1. So if K is more than 1, so it's 100, or it's 1,000, or it's 1,000,000. Sorry, I was looking for the questions we just did. Like here, we got K was equal to 50.5. You're going to see K's, these are exponential numbers. They're going to be huge or small. But if K is greater than 1, that must mean that the products are greater than the reactants, that it is product favored, is what we say. So again, it's a ratio. It must mean that the numerator is larger than the denominator. So equilibrium does not mean 1. If you get a K equal to 1, that's like, I don't think I've ever seen that, where the products and reactants are equal. So it just means there's more product. So with that, if K is less than 1, it must mean that you have more reactants, that the denominator is the larger number. And so we would say it's reactant favored. And if you look on the previous page, that's like question number 2. So on question number 1, we got 50.5. And then question number 2, we got K was 0.00408. So on the first one, we have more product. On the second one, we have more reactant. K's vary ginormously. We're going to see some outrageous K's this term. We're going to see like K to the 5.2 times 10 to the negative 32. Sometimes they're really large and really small. For example, on this next one, this K value, it's just a little bit under 1. It's 0.1, but it is less than 1. So this would be reactant favored. On this one, K is 50, so it's just above 1. So that one is product favored. If you like look ahead 2 pages, this is the page where they become ridiculous. Like this number. K is 6.3 times 10 to the negative 58. I like look at that number. Can any of you really conceive what that number means? That's like 57 zeros, 0.000000000. So that's saying it's pretty much all reactant. This is extremely reactant favored. Or if you get like here, it's 10 to the 30th down here. So this is saying it's very product favored. So again, it's just a balance point. So here, if K is ginormous, like that 10 to the 30th power, or like Avogadro's number, like 10 to the 23rd, blah, blah, blah. I don't like writing a number there, but that means that you have so much product that we just say it's an arrow, it goes one direction, that we say it's pretty much one direction. This is what you did for 2 terms. Like all of our arrows only went one way, that we made an assumption that it pretty much was a one-way reaction. In this case, this one has so little product. Basically, there's no product, that we say there's no reaction. Now, I want to comment on this. In here, because we're going to have numbers and we can do the math, you're going to either say it's product favored or reactant favored. So we're going to go with these answers. You can then like write me a nice long essay and say, yeah, but this number is so ridiculously large. It's really, even though we're saying it's product favored, it's really one way. And that's great, but that's all I'm looking for, is that you're saying K is greater than 1 is product favored, K is less than 1. It's a ratio. That's important. All right, we're going to do one more type of reaction, and that's the reaction quotient, which is Q. And there's all these gimmicks for how to do this, and I had a student who showed me a really cool way. This is where, let's just do the problem. All right, here's our equation. We have 2 moles of hydrogen, 1 mole of nitrogen, 2 moles of NH3, and they're all mixed. So technically, this is our initial. So all I'm going to do is write each number under the correct component in my equation. When you mix something, that is your initial. So if the question's saying you're mixing or it's put in the test tube or something like that, That's your initial amount. So my hydrogen is 2.0. And remember, in the chart, you have units. So moles. And the units have to be molarity. So we're going to have to find our volume. Oh, I was so nice to myself here. It's per liter because it's 1 liter. All right. Now, somebody can be a stickler for Sig Figs, and technically that 1.0 liter would mean that my final answer should only have 2 Sig Figs, which isn't going to matter because the question isn't actually asking for a number. All right, so here's the question I have for you. Where's the 0?
Nitrogen? Where's nitrogen?
There are no zeros.
There's no zeros.
Right.
Does 0 get an E like that, or does it just be an S? I don't know. So I'm not an English teacher. That means if there's no zeros, it's a Q problem. And that is like happy dance time. Q problems are students' favorite problems. I moved it to the end of today's lecture because these are like, yes, it's not an ice chart. It's not an ice chart. We have all the initials. There's no zeros. We don't know which way is the plus and the minus. So instead of K, we solve for Q. And that means we're going to plug all the initial numbers in. We have to write our Q expression. It's the same as our K expression. So it's still products over reactants. So NH3 is our product. So that's on top, squared. And the nitrogen and the hydrogen is to the 3rd power. All right. And now we're going to plug in all the initials. So for Q, you plug in initials. And again, they have to be molarity. Or if we're working with KP, we would do ATMs, which you might run into that in the study set. So here we go. So we're going to have 2 squared over 1 times 2 cubed, which is 4 over 8, right? 2 squared is 4, 2 cubed is 8. So anybody know 4 divided by 8? You always have your calculator if you don't know what 4 divided by 8 is. I asked somebody one year and they got really mad at me because they thought I was insulting them, but I'm hoping that you can all solve for 4 divided by 8 as this is 1/2 or 0.5. And that's our value for Q. All right, so the question didn't ask us what is Q or what is K. In fact, K was given up here. K was given to us. What the question asked us for is, will more NH3 form? It's really a yes-no question. So this was a trick I had a student show me, and I absolutely love this. It does require that you pass kindergarten, which means that you know your ABCs. So if you sing your ABCs, which is very relaxing, which comes first, K or Q? So K comes before Q. This is where I know who watches like my lecture and who goes to Khan Academy, because they do it not this way. Kind of back to your question, Elizabeth, can you have fun when you do your presentation, please? Everyone wants you to have fun. Put them in alphabetical order. Now, K was given to you. K is 0.105, Q is 0.5. Which one's larger? You're going to make your greater than or less than sign. So Q is larger than K. So I taught my son, homeschooled him. So when you teach greater than, the alligator eats the bigger number. All right, this is the part that's really cool. The nose points in the direction. So the arrow is going to go that way. So you see how the nose is pointing? The alligator's, actually that's not his nose, but the arrow's going that way. Or you can just memorize it, and you guys, right, you can have your notes. If K is less than Q, the arrow goes reverse. You can also just write that. Okay, if K is less than Q, it goes reverse. But that remains that you have to always look through your notes, or you can sing the alphabet song and smile for a moment. So let's answer our question. Will more NH3 form? Well, this is the arrow. We didn't have a 0. It's going to go this way. So the answer is no. And it would ask you to explain. This is the explanation. Q equals this. K is less than Q. The reaction goes reverse. No. We're going to get more nitrogen and hydrogen, and we're going to get less NH3. All right. So I'm going to pause this and give you like 2 minutes. See if you can solve this one. It's on the page under Q, so see if you can get that. All right, I'm going to solve. If you're working on it, just keep going. So let's plug our, we don't know it's a Q, let's like we're doing the homework. It's not going to say, hey, this is a Q problem. So you have information and says, okay, I mixed all this stuff. So this is my I. So I have 0.020 moles. The chart has units. Keep that in mind. The chart has units. My hydrogen is 0.010 moles. My iodine is 0.010 moles. Now, there is another comment I need to make real quick. So when you do the study set, most students, you guys can go like anywhere now, right? You can go and print. It can be helpful to have the study set printed and to do your work on the study set, but there's always some students who are like, I don't print. You can do it on notebook paper, and that's fine. Just have it in the same format. And then some students are like, there's just not enough room for me. That's fine. Then do it on notebook paper. When you submit your stuff, you all know how to take a picture in a scanned format, and it has to be one document. So if it's multiple pages, great. The numbers are really weird because me and Bill Gates are challenged. So just keep your numbers the same as mine. If you just do it on notebook paper, you can absolutely do it on notebook paper, or you just learn to write smaller. All right. And the other comment I made is when you submit it, it's one PDF form. It has to be a PDF, because then I can see it. We'll work out. You should have all learned how to do that with your other teachers. And we're in 2 liters, so we're going to divide by the 2 liters. I like to always use, especially when I'm teaching, I have to use the numbers that are given in the problems. This is going to be 0.005 molar. All right, these are my I's. I have no zeros, so I'm not going to do the rest of the chart. I'm going to solve for Q. You state your Q formula first. So it's the same as your K formula, products over reactants, and then we just plug in. It has to be molarity, and the chart has to show the units. Some students show the units in their K. I would prefer that you did. I'm like trying to rush for time at the moment, because that helps you to remember it has to be molarity. But if you leave them out, that's okay. They have to be in the chart. All right, you solve for Q, it equals 4. You alphabetically, K is 50. That is greater than Q, which was 4. So it's going to move forward. So if K was less than Q, it went reverse. K is greater than Q, it goes forward. I personally never remember that until I do my alphabet and the alligator's nose points you forward. I had a student teach me that trick and it works. And so whenever you do a Q problem, this is all the explanation I need, but go back and see if you finish. Is the system at equilibrium? It's going to usually ask you what happens to reach equilibrium. And so that's fine. The arrow's saying it shifts forward. So this is saying, I don't need the words. Some of you need the words. It shifts forward. to attain equilibrium. So we could technically go and finish the chart. So that would mean this would be minus x plus 2x. And then you could finish and solve for your x values and find what your numbers are. Any questions?
So we don't do anything with the temperature, right?
Nope. So temperature, again, actually that shows up on the next page. So perfect timing. K is temperature dependent. So about half of the problems are going to give you a temperature. You're going to ignore it unless it's one of these, unless there's 2 times you're not going to ignore it. One is in the Le Chatelier's problems, which is our next page. And the other time is this is 223. And so we're going to run into on the worksheets. The worksheets are fun. Keep that in mind. And the worksheets bring back things that you learned in 221 and 222. You guys remember PV equals nRT? So there are times where I will give you pressure, volume like that, and you have to change it back to molarity or vice versa. So if you're doing PV equals nRT, you'll have to know the temperature. And those show up on worksheets. All right. So we're going to start this page, which is Le Chatelier's principle. So this is another key concept from this term. And we're going to talk about it today. It's not on the first study set. We're going to talk about it more tomorrow. It is on the second study set, and I think everyone after that. It can be a little bit funky when you first hear it. So he is a famous chemist. There's not a lot of information about him because this is the only thing he did. And he wasn't quite the character like Linus Pauling. It's great. He's already picked. So some of these people, when you pick your famous chemists, and you can change your mind. So you can send me an email or just talk to me during office hours to get your famous chemist. But you can pick him. Sometimes there might be something that nobody's found out about him. You know, and you can dress up like your famous chemist when you do your presentation. So if you want to sport those kind of glasses that were popular at one time. So stress, we are actually chemical equations. And so whenever you stress or disturb a system, the key here for Le Chatelier's principle is the system is at equilibrium, which again is attained as soon as you mix the stuff. As soon as the stuff mixes, that initial is for a femtosecond of a time. The system has to adjust because it has to be at equilibrium. So it's always going to kind of deal with what the stress is, and it gets you back. That's what our body does with different stresses. So one of the things, and these again are things students have shown me that help them, is everything is in a test tube. It is a closed system. So all the components are there. So something that can help you, some students will, for their equation, put their equation in brackets around the whole thing. So this is all in one test tube. So basically in our test tube, that's why I'm not an art major, we have the calcium, we have, you may know HCO3. We deal with that one a lot when we get to bases. That's bicarbonate, baking soda. You're going to have the solid calcium carbonate. That's our calcium carbonate. The solid has to be there. You have CO2 gas bubbles forming. So there's going to be a cork on this, because if there wasn't a cork, the CO2 would escape. So everything has to be there. The CO2 is being kept in there. And of course, this is all in water. So everything's there. We're at equilibrium. And now somebody tweaks it. So they add more calcium. So if you add the calcium, the system has to use what you added to get it back to equilibrium. So you can't have extra calcium there. So what's going to happen if we add the calcium? It's going to shift forward. So what's going to happen are shifts. It's either going to go forward or reverse. So if you add something, you have to use it. So when you add, it must react. I don't like all these words, but I have found some students like the words. So if the words help you, great. All right, so now we're going to remove something. So the CO2, I'm going to write it over here. I'm going to take the CO. So basically you take the cork off, the CO2 leaves, it's a gas. If you are missing something, so if you remove, you must make more. You can't add more, you must make more by reacting. So when you take something away, this one again shifts forward. The principle of Chinese, I actually have a degree in Chinese medicine. This is how the whole yin yang thing, everything balances. So in Chinese medicine, somebody comes in and we readjust their balance point. Very different from how allopathic medicine works, which is they just slap something over everything. So we mask it. So it shifts forward because we have to make more CO2. So it doesn't completely react. It just shifts enough. K stays the same. So K does not change. K is a constant. So everything has to shift to keep the equilibrium the same. All right, here, if we remove the bicarbonate is on the reactant side. So it has to shift reverse to get there. You don't have to write the word shift. Just use the arrows. When you use arrows, it's going to work better. So it's shifting reverse. The other term is, if you don't use arrows, is use the words forward and reverse. All right, so the last one is that we add the calcium carbonate. So what's going to happen?
Nothing.
Nothing happens. Why?
It's a solid.
Yeah, so if something's a solid or a liquid, there is no change, or nothing. You can say nothing. So thank you, Christian. That was awesome. So if something's a solid or liquid, if you remember, the very first thing I said is before you do anything, cross out the solids and liquids so that you don't try to do anything with them, especially in Le Chatelier's, because that will help you. But also when we do write our K expression, they don't affect anything. They're not part of our ice charts also. So if you have a solid or liquid, we don't have to worry about them in the ice chart. It's only the aqueous and the gases that we worry about. So that I did that on purpose for that. All right. Sorry, I'm trying to decide if I want to do the next one or show you something on the next page. All right, we'll try it. So our fine fairy is going to remove the hydrogen. So again, something that can help. You don't have to do this, but for some students, the brackets make a difference. And back to the comment, H2O as a liquid, it's not going to matter if we add the H2O. So I want to go back one step to the answer to the question that Christian answered. If I add more calcium carbonate, it's not going to matter, because if you're at equilibrium, that term at equilibrium means there is solid calcium carbonate. It doesn't matter how much, as long as there's one crystal. However, if they remove the calcium carbonate, so there was none in there, the equilibrium would have to shift to make it, because you can't have a zero at equilibrium. So just be careful of something like that. All right, so our fairy removes the hydrogen. So if you take away, that means that we have no hydrogen, that this would be a zero. Basically, when we remove it, it means you have a zero. So the reaction is going to go which way? This is where in class everybody starts like putting their fingers, their thumb one way or the other. It's going to have to move towards the hydrogen, so it's going to go reverse. So here's your arrows. And so if you take something away, the arrow is going to have to go. This means that this was a 0 on our equation. And so it's back to like the ice charts. It's just we're doing it mentally. All right. Mischievous Gnome. So if you don't know what a gnome is, go ahead and Google it. He adds more water. So be careful with this. H2O sometimes will be a gas. If it's a gas in the equation, it would have an effect, but it's a liquid. So no effect, so no change. All right, and now the evil gremlin sits on it, and so he's increasing the pressure. So he's increasing the pressure when he sits on it, because when he sits on it, he's squishing it, which means he decreased the volume. So remember when you did gas laws, pressure and volume are always opposite. That is true with Le Chatelier's principle. Pressure and volume are always going to be an opposite. So if one goes up, the other goes down. So if there's less space or greater pressure, you have to look. So for C, look at moles of gas. So on my reactant side, I have 4 moles. So you're looking at the stoichiometry. So I have 1 plus 3. And on my product side, I have 1 mole. So logically, you have less space, the volumes decrease. It's going to move to the side that has less. 4 moles is good. It's like people. 4 moles is going to take up more space. So if you're in a house with 4 people, you're going to need more space. If there's only 1 of you, you can live in a little space. So this is going to shift forward. So to the side with less moles of gas. Again, Le Chatelier's, it just takes practice. We'll see some tomorrow also. All right. So heat, ice. So Santa's Elves plunges it into ice. To do this one, we get to go and look at, do it in blue. You guys remember that symbol? What does that mean? This one's worth a bonus point if somebody can remember.
Change in enthalpy.
It is. So what does it mean for this equation? What does that tell us?
Endothermic.
It is endothermic. I don't know who said that. They're not going to tell me who said that. So endothermic means, you can just say endo. So remember delta H, this means delta H is greater than 0. So delta H's can be greater than 0. They can be positive or negative. If it's greater than 0, it means it's endothermic, that it's absorbing heat. We do a lot with endothermic, exothermic this term. So if you didn't really like it in 221, you're going to actually find that, what was the big deal? It's like your best friend this term. So it absorbs heat. So one of the ways to think about that is that heat is over here. It's a reactant. Heat is being absorbed into the reaction. And so if we put it on ice, that means it's got to move in the direction to make more heat. Because it's like when you're cold, what do? You want to turn on the heat. So this is going to go reverse. There's another trick. So what happens is about half of you are good with that because your brain thinks that way. You're like, well, yeah, that's logical. If I put it on ice, I'm going to have to move in the direction towards the heat because it wants to stay at equilibrium. It wants to stay at the same temperature is one way to think of it. So it's going to move towards the heat. If you heat it up, it's going to move away from the heat, kind of like what happened to all of you when you got the 117-degree day. There's also another trick that the other half of you are going to do this. Endothermic likes heat. So since endo absorbs heat, whenever you add heat, it's going to move in the endothermic direction. Here we're putting it on ice. So if you're taking away heat, that's what exothermic means, is it's releasing heat. So it's going to go in that direction. I don't know. It's some people one way works or the other, and you're going to figure that out this week. All right, let's do 2 more here. Which ones will increase the concentration of the carbon monoxide? So the carbon monoxide's over here, anything that would shift it reverse. So any shift reverse, because that would move it towards the carbon monoxide. So if we move towards the carbon monoxide, we're going to have more of it. So that would have been A and D. So we would just say A and D. Does that make sense? All right. And now this is kind of the question back to what Major had asked a few minutes or like a half hour ago. So this is where temperature is going to be important, is Le Chatelier's. And temperature, you can only do things with temperature if you're told the delta H. So if it's exo or endo. Pressure and volume are going to always be related, but temperature is based off, for temperature, look at exo endo. So look at the delta H. So for D, you're going to look at the delta H. So what conditions will maximize the CH4? So CH4 means we want to move it forward. And this is usually how it's worded, that reactions are written for what that person is trying to do. So we're trying to make it go forward. And so temperature, we want it to go forward. We want a high temperature. Because when we put it on ice, it went the wrong way. So we want a high temperature. Endothermics like high temperature. They want to absorb the heat. All right, pressure. When we increase the pressure, it also, so a high temperature shifts it forward and a high pressure shifted it forward. That's going back and looking at C and D. The thing I want to emphasize on F, temperature and pressure are not related in these problems. That's not the best way to explain that, but they're not related. It's not gas laws. Pressure and volume are. That's from gas laws, but the temperature is from the endo-exothermic, which is something that gas laws doesn't take into effect. So temperature is based if it's exo or endo. Pressure, volume are related based on gas laws and the number of moles of gas. And we'll do this one tomorrow. The Chatelier is not on your first homework. And again, your first homework isn't due till 6, but I'm going to stop recording unless there's a question for the good of everybody.